All right, so our next subject is things called predicates and quantifiers. And we've sort of encountered these already, but I'm going to make them a little more formal now. So we're going to be dealing with things like this upside down A, followed by the name of a propositional variable. This is called the universal quantifier. And we can interpret it as saying for all x. And the backwards E followed by an x, or followed by a symbol, is called the existential quantifier. And we can interpret this as saying there exists an x. Or perhaps we could say for some x. And these are useful for building propositions out of other statements. So for example, here's a proposition. For all x, x is less than 0, or x is equal to the absolute value of x. And we need to be a little careful about universes that we're talking about here. So we might actually want to say for all x contained in Z, and then we could say x is less than 0, or x is equal to the absolute value of x. And this proposition happens to be true because we know that if a number is not negative, it's 0 or positive, and it's equal to its absolute value. So this proposition is true. But this is also a proposition for all x contained in Z. X equals 2 times x. It's a proposition. Is it true? No. It's not true that for all x. On the other hand, there exists an x contained in Z such that x equals 2 times x. That is a true proposition. And usually when we write an existential quantifier, we use either a colon or maybe a vertical bar followed by the actual proposition. And these symbols we interpret as such that. So this is the proposition. There exists an x in the set of integers such that x is equal to 2 times x. Is that proposition true? It is, because if x is equal to 0, x equals 2x. So the fact that there's a single x for which this proposition is true means that this existential quantifier in front of it, this is a true proposition. But saying for all x, x equals 2x, that's clearly false because x is an element of the integers. 1 is an element of the integers, but 1 is not equal to 2 times 1. Okay? But these are all propositions. They're declarative statements that have truth values. All right, let me show you some other examples. For all x, x squared is bigger than or equal to 0. Is that true? Sure. For all x, it is not true that x is equal to the absolute value of x. And that's false, right? If x is equal to a negative number, then this proposition is true. X is not equal to the absolute value of x. So saying that this proposition is false, saying that not is true, fails to be true when x is negative. But certainly there exists in x such that it's not true that x equals absolute x. For example, the value x equals -1. -1 is not equal to 1, so this is false. The negation is true. So this proposition is true. This proposition is false. All right, now we can apply operations to these quantifiers and start to get even more propositions out of it. So suppose let P of x be some proposition. And suppose we have the proposition for all x, P of x. Well, the negation of this proposition is the following. There exists an x such that not P of x. And if you think about it, what does this mean? This means that any x that you pick, p of x is going to be true. This is saying there's at least one x where p of x is false. So this and this are complements of each other, right? The negation of this is here, and the negation of that is here. And similarly, saying there exists an x such that p of x, the negation of that is for all x, not p of x. This says there's at least one x where p is true. The complement of that is saying there's no x where p is true. In other words, for all x, p is false. All right, and a notational thing that we might do, for example, we could say for all x contained in a set of natural numbers, p of x, and this means, and let's suppose 0 is a member of the natural numbers, this means that when x is 0, p of x is true, when x is 1, p of x is true, and so on. This means p of 0 is true, and p of 1, and p of 2, and etc. And there exists an x contained in the natural numbers such that p of x means or is logically equivalent to p of 0 or p of 1 or p of 2 and so on. Because this is saying there's some natural number x where p of x is true, and this is saying that if we write this out for all the natural numbers, at least one of those is true. So these really mean the same thing. All right, so we'll work out some problems on the board, and we'll see some of the deeper details of these quantifiers.